So today, inshallah, Shabab, we will continue our discussions on speed control. Last class, we discussed the adding resistance, and regarding the problem, we discussed this table last class. طبعا this table is nothing but a comparison between two relations, Shabab. We have the torque relation, which is the machine relation, and the other relation is the load torque relation. We said we may have many types of load torque. Here, for instance, we are going to consider three types, just for instance, just as examples. Okay, for instance, for T constant, which means T1 over T2 is unity, constant load torque. We may have torque proportional to speed, which means if the torque increase, the speed will increase. If the torque decrease, the speed will be decreased. Time. What is the relation between torque and speed now? You know, speed omega is nothing but the relation between slip and synchronous speed. صح يا شباب? So we can say, for instance, N equals 1 minus S multiplied by NS. And you know NS equals 120 F over number of poles. So finally we can say N is proportional to 1 minus S multiplied by frequency over number of poles. This is now the relation or change or parameter that affecting N. So if we can say torque is proportional to omega or proportional to N, this means T1 over T2 will equal to 1 minus S1 multiplied by F1 over B1 divided by 1 minus S2 multiplied by F2 over P2, which will be in the numerator. تمام يا شباب? Is it clear? This is now the curve of load. This is the load curve now. Now we are speaking about the load curve where T is proportional to omega. Right. If we have fan load torque, where torque is proportional to omega squared, we will just square the right-hand side part here in the equation. So the relation will be 1 minus S1 F1 P2 all squared, and so for the denominator. Fine. Now, this is regarding the first row here is regarding the machine, the load curve. Regarding the machine curve, we have many types or many parameters to change the curve, which are the parameters of speed control. We discussed previously, Shabab, that torque at small slip, which is the part of the characteristic that we need to move or change in order to make speed control. Torque is proportional to V square S over R2 prime omega S. This is when we neglect the value of X equivalent compared to R2 prime over S, and also neglecting R1. تمام يا شباب? This is approximated relation. In this case, when we compare the relation of torque for the machine characteristic, we can say now T1 over T2 and start comparing these parameters. So it's V1 squared multiplied by S1 over R2 prime at case number 1 multiplied by omega S at case number 1. طيب omega S يا شباب here, omega S, it's similar to synchronous speed, so it's proportional to F over number of poles. So we can replace omega by F over number of poles as well. So when you compare now two different values and changing the parameters here, we can find this relation now. T1 over T2 equals V1 square S1 P1, which is the number of poles, F2 multiplied by R2 prime plus R add. Both here are considered as the resistance at the added value case. Okay. And the denominator will be V square S2 V2 square S2 P2 F1 R2 prime, which is the resistance of the rotor in the first case. So يا شباب, whatever the load type, this will be the relation of the speed control now. So at different speed control, we should start finding the parameter that we are going to control and compare it with the load characteristic. So for instance, let's have frequency control, for instance. Apply here, Shabab, frequency is going to be changed along with S. S all of time will be changed because this is the factor that representing speed. So when we make speed control by frequency, this means that all other parameters will not be controlled. So we should remove P1 F2 or PF from equation, either 1 or 2 طبعا. Okay, so we will remove P, sorry, not F, we are going to make frequency control, so we'll keep F. We will remove V, we will remove R. So the relation of the machine now will be only S1F2, as you can see here, S1F2 over S2F1, which is the relation of T1 over T2. So this now representing the machine. What about the load? Here, in this case, torque load is constant, so we can say this relation is equal to 1. If we apply it for torque proportional to omega, so start in the relation here, change the value of F only and keep and remove others, where here يعني B can be removed, so we can remove B, and we can say now this relation S1 F2 over S2 F1 will be constant, or sorry, will be used for all type of loads. However, here for torque proportional to speed, we can say now it's 1 minus S1 multiplied by F1 over 1 minus S2 multiplied by F2. You got it, Shabab, how we can get the relation or the two relations of the machine and load according to speed control technique? Is it clear? This is very important, Shabab, to solve problems in order to understand how we can solve problems. It's not easy to memorize all of these equations. You can add it in your formula sheet, or you can just deduce it as we have made now. But I know in the exam there will be time may be limited, or you may be stressed. So I recommend to add it to your formula sheet. Fine. So we discussed the added resistance, Shabab, and we started in the previous class in the solved problem. Today, inshallah, we will continue solving the problem on adding resistance, and we will discuss the voltage control, and if we have time, we will discuss the frequency control as well. So let's continue our example. We said last class three-phase.
Doctor.
Fadal.
Someone is raising his hand.
اتفضل يا باشمهندس. يا شباب انا مش شايف طبعا السكرين. if you have a question just ask, don't raise your hand. اتفضل.
Yes, doctor, actually I wanted to ask, I didn't find this slides just to
sorry, I just updated this today. I shared you last class, it was in separate Word file. I just updated before of the class, so I will send it to you inshallah after the class. Okay?
Doctor, because I wanted to go through it, and if I have any question, because just it's not that clear for me.
Let's discuss the table again. We have now two relations, Shabab. We have curve relation, curve of the machine, which is this relation now, torque and parameters of the induction motor. And we have another relation, which is the load torque. We said together before, the operating point of any machine is nothing but the intersection between two curves, machine curve and load curve. Okay? So we have like that, Shabab. We have, this is speed or S and torque. So this is now considered as the machine curve. Load torque may be constant load torque like that, maybe fan load torque like that. Okay, so the operating point will be the intersection between the 2 points. صح؟ طبعا we have only one load, it's not two load, but I just discussing if we have different load types. So if we have fan load like that, and this is the machine characteristics, so the intersection point here will be the operating point. So this means if I have the relation of T for the machine and equalize this machine equation to the torque speed characteristic also, this is going to give me the operating point. This is what we are going to do here. We are comparing or equalizing two relations, which are load relation and torque, load relation, torque speed load relation, and motor relation. These are the two relations. You know the motor relation is that one. And the torque relation, it may be constant, it may be T proportional to speed, it may be T proportional to omega squared, or maybe any other relation. Whatever the relation, it will be given in the exam if it is different. Okay? So, in this case, Shabab, how we can get the or make the speed control by any type of machine, by any type of speed control techniques? Simply, you should compare two before and after control, just by comparing T1 and T2. We have now 2 points, which means, for instance, if we now, for this characteristic, we move the characteristic by adding resistance like that. So the new operating point will be that point. How can I get this point? I should compare point number 1 with point number 2. So it's nothing but comparing the torque at added resistance with fan load. So how we can use the relations now? Torque with fan loads, this is the torque with fan load. Torque with added resistance, this is the torque with added resistance. So the intersection in the table here, we can use this relation. This is the way. How we can get this relation, ya shabab? Again, first, start with the torque equation. Apply the speed control technique. You are going to add resistance. So the variable here will be R2 prime. And all others will be removed from the equation. Only S and T will be there. So now we can say T1 is proportional to T is proportional to S over R. So we can say T1 over T2 equals S1 over S2 multiplied by R2 over R1. R2 here means resistance in the second case, which is nothing but rotor resistance plus added resistance. And R1 means resistance in the first case, which is only the rotor resistance. Okay, Shabab? So we can say here, for instance, the relation will be S1 over S2 multiplied by R in the second case over R in the first case. If we have fan load torque, so we should say this equals what, Shabab? Is equals unity? Unity is only for constant load torque. So it should be this relation, because we have here fan. Fan, which means torque is proportional to omega square. And we said omega is a function of 1 minus S multiplied by F over number of poles. Right, here we are going to add only resistance. So F and B will be constant. So we can say N is proportional to 1 minus S only. Sorry, but here is square. So N torque is proportional to omega square. So we can say T1 over T2 equals N1 square over N2 square. So we said here 1 minus S1 square over 1 minus S2 square. So this is the way, Shabab, how we can construct this table, or how we can extract the proper relation in order to solve our problem. You got it, Shabab? Is it clear?
Yeah, now it's clear.
Yes.
Okay.
Doctor, the intersection has to be in the right, right?
The intersection of what again?
Of the load curve, of the load and the motor.
For all of these relations, all of this white area, okay, the right hand side relation is the load torque relation. The left hand side is the motor relation.
Yes.
Okay.
Okay.
تمام. يعني I wish this is يعني to be clear, because this is very important to recognize the different different way how we can solve the problems with speed control. يعني otherwise, if you did not do that, يعني it will be very difficult to solve your problem. So we discussed, Shabab, the added resistance. Let's continue solving our example here. We have 3-phase star connected 30 horsepower. This is the output rated power. 480 volts. This is a line-to-line supply voltage. 6 poles, 60 hertz slip ring induction motor. Has a stator resistance, R1 is given, 0.5. Rotor resistance referred to stator, R2 is given. Rotational loss is 500. Core loss is 600. Assume that the change in the rotational speed, losses due to the change in speed is minor. So the rotational loss is constant, whatever the speed. Also, the motor load is constant torque. So here we can say for all of cases, T1 over T2 is unity. Now, at full load torque, calculate the speed of the motor. So we solved this part last class. In order to calculate the speed of the motor, now we have the power, Shabab. So we can say P developed equals P out at rated plus rotational loss, which we have already. So we can get P developed and compare this with the torque at small slip, because this is all of time will be the relation of torque at speed control, Shabab, which is torque at small slip. So we can say T1 over T2 equals, give subscription for all of these variable type. So from now, Shabab, we can say if we need to calculate slip at certain value of power, so we can say torque developed multiplied by omega equal to B developed. We have power. Okay, and we have the relation of torque. Okay, so we can say now it's equal to approximately equal to v square s over omega r2 prime multiplied by omega. So here we have omega, here we have omega s, so we can use the relation omega equals 1 minus s multiplied by omega s and remove this from the equation and add only 1 minus s. So now you have power, we already obtained, and you have v, r2 prime is given, so the variable s will be obtained from here. This is s, so you can get the speed easily. This is now the motor speed. Next, it was required to calculate the value of added resistance. What will be, or calculate the added resistance to the rotor circuit needed to reduce the speed by 20%. Also here, Shabab, I modified a bit in the order of the solution of this example, and it was arranged in a different way. I will update inshallah you after this class. You will find 2 slides after that if you have the old version. The value of R added, how we can get it? طبعا simply شباب, as we stated in the table, how we can use speed control. Now we are going to make speed control. We are going to reduce speed by 20%. Okay, and we need to calculate the new value of R add. So we can say شباب, T1 over T2 equals the relation in case of constant load, which is S multiplied by R2 prime plus R add. This is the resistance in the second case. This is the slip in the first case, over S nu multiplied by R2 prime. This is equals unity because we have constant load torque. So now you have S new, S old. S new you can obtain. How we can obtain S new, Shabab? Simply you have the new speed, which is new speed.
120 multiplied by the frequency over number of poles.
Exactly. We don't need to do that. We need only the speed of the rotor, not the synchronous speed. Now you have the old speed, which is 1150 RPM. So we can say N new equals 0.8 multiplied by N old, because we reduce the speed by 20%. So it's nothing but 0.8 multiplied by 1150 RPM. This is now N. So how we can get S? Simply we can say S equals NS minus N new over NS. So getting the value of S new, Shabab, this is S new. After getting the value of S new, it will be very easy to get the value of R add. So this is now the value of adding resistance. Fine. So now we use the speed control characteristics to get the value of adding resistance. Here in this problem, Shabab, it's very important. It reflects how the machine will be efficient if we add the rotor resistance, and it's reflected also in the cost of energy during a year. It will be very important, or even we will see for which long period. Calculate the motor efficiency without and with added resistance. Now you have all of parameters to calculate everything. You have R, because you get the value of R added. So you know now the equivalent circuit before or after adding the resistance, because we have all of values. So easily we can get the value of current, because we have the power developed and we can obtain the value of current from the power. And after that, we can start calculating the efficiency. So you can get the efficiency easily for the 2 cases. We'll discuss it now and compare it. And also after that, if the cost of energy is $0.05, which is 5 cents, $5 per kilowatt hour. This price is very old, Shabab. And this example from the book of Dr. Sharqawi, it's long time ago, and this book is old a bit. So the price of electricity is much higher than this time, maybe 6-7 times of this value. Compute the annual cost of the operation or of operating the motor continuously. Continuously, it means it's working 24/7 with the added resistance. Assume that the motor operates 100 hours a week. Here it's continuously, but he gives you the value of hours, so we can consider that this is the per week hours. Okay, fine. For that, Shabab, this example is very important. Let's see together. Start with firstly with the efficiency, and after getting the value of R add, we need to calculate efficiency. We said simply we can compare P developed equal 3I squared R over S multiplied by 1 minus S. So this is now here representing B mechanical يا شباب. تمام؟ B mechanical, which is calculated previously. It was 22,880. So it's equal to 3I squared R2 prime over S multiplied by 1 minus S. So you can get the value of current here. So this is now the value of current. Why we need the current, شباب? We need the current in order to calculate the copper loss. We have resistance R1 and R2. So simply multiply 3I squared R1 plus R2 because we use here the approximated equivalent circuit. تمام? So this is now considered as the copper loss of the machine on rotor and stator. So simply you can say now input power equal developed power plus winding loss, which are copper loss, plus core losses. So we can get the input power, and simply we have the output power. We can calculate the machine efficiency. So the efficiency without adding resistance is 86. Let's see together at the other case. طبعا this is just to compare the new value in order to get S new. We already solved this before. We need now to calculate the second case after adding resistance. So we can say يا شباب B developed new over B developed equals torque developed new multiplied by omega new over torque old multiplied by omega old. This is because you know P is or equals torque multiplied by omega. So now يا شباب we have constant load torque, which means TD new and TD are equal. So we can say power new over power old equals omega new over omega old. So simply we can compare. We have the omega or speed at before and after adding resistance. So simply we can get the value of power developed new. After getting power developed new, we can calculate the current by the same way يا شباب. But here we have to consider the value of R add. تمام? So getting the value of current here, you can calculate also the copper loss in the same way, but here you have to consider adding resistance value with the copper loss. So this now will be the copper loss, شباب. As you can see, copper loss here is 6.5 kilowatts. If we return back again and compare this with the copper loss before of adding resistance, here it was 2.5 almost. صح؟ صح يا شباب؟ So it's more than 2 times يا شباب. The loss or the winding loss is more than 2 times now. So the input power is nothing but also again the developed power plus core losses plus copper loss. So we can get the overall input power, and you have the machine output power. You can say output power equals to mechanical power minus rotational loss. You get the mechanical power, and you have the mechanical loss as constant power. So we can get the output power now. So we can calculate the efficiency in the new case, and you can see it's now 70%, which means the efficiency has been decreased. Why? Just because we added resistance in order to make speed control. So is it going to be يا شباب all of time, or it's just for transient period? ها شباب, speed control, is it going to be for certain period, or it will be for all of time during speed control? يعني this added resistance will be added only for few moments, or it will be there if I need the new value of speed?
It could be continuously there.
Exactly. So this is now our problem, which means we will have small efficiency all of time. So this is in terms of the performance. What about the cost now? So let's see the cost together. In order to calculate the cost, شباب, you know, we need to calculate the added power, which will give us the added cost. Now we need to calculate the energy according to what we have. We have the cost per kilowatt hour يا شباب, صح? So the cost here, cost per energy, which is joule, or in kilo. So let's say kilowatt hour. This is the cost what we have. So in order to get, sorry, this is the price or tariff what we have. In order to get the cost, we need to multiply by what? By the energy, which means power for certain period. So let's calculate together the power consumed on the resistance for a certain period. طبعا P added equal 3I square R. This is the power. So the power is 4.568 kilowatts. This is only power, but we need energy, so we should multiply this by time. What is the time now? The total hours, what we are going to use, which is T for 1 year. It's stated that it's 100 hours per week. 100 hours per week. 100 hours, and we have 52 weeks per year. So the number or the total number of hours will be 5,200 hours. So this is now the time. If you multiply this by the value of power, it will give you the energy. Then multiply by the cost, which is 5 cents, so you can get the value of or the amount of money that are going to be used just only if you added resistance. So this is the cost now of speed control. Can you see? For 1 year, we added more than $1,000 just to make the speed control by adding resistance. So it's a costly technique, and at the same time, it's reducing the efficiency. So you have bad performance compared to other techniques. So this is a very practical example, شباب. Actually I like it because it's touching the actual life for the machine applications. Do we have further?
I think for the power added, it's not this number, it's not exactly, because we should add even the current new passing through the old resistance.
We don't need this. We consider only here, this cost here is the cost of the added resistance. However, the resistance of the motor itself, it exists whatever you control speed or not. صح ولا غلط?
Sure, but the current will differ.
What's the problem? You now consider only now the case of added resistance, which is at I2 new. This is the current for adding resistance. And what we need to calculate is the cost of adding the resistance.
No, my point actually, we can add one term, which is 3 multiplied by high current, the new current minus the old current, multiplied by the exit resistance.
No. This is not actual. What is the power on the added resistance? Is it I2 in the second case, I2 new minus I2 old? This is not the actual current in the added resistance. The actual current is I2 new.
Sorry, doctor, actually, I know, but I wanted to make it for more exact. The current actually, once we add the resistance, the current is changing. Am I right?
Which is the new value. If we added the resistance, we will have the new value of current, which we have already calculated. Let's see again here. I2 new is 25 amperes. So this is now the current when we added the resistance. Before of adding resistance, the current was 28.8. Okay? So what we should make in order to calculate the cost due to added resistance, we should use the current of the case number 2, which is 25 ampere. صح كده?
Yeah, I agree. Can we say that the added cost will be the P old, the P addition minus, or the P new minus the P old? Can we say that?
P new minus P old?
Yes.
Let's write it now. P new, which means I2 prime square multiplied by R2 prime plus R1 plus R add. This is the new power, صح?
Yes.
P old means let's say I1, which is case number 1. I1 square multiplied by R1 plus R2 prime. صح كده؟
Yes.
يعني you would like to say we should say P old minus P new
Yes. This
in
is
order
my
to get the difference.
Yeah. Is it right?
It's now comparing. يعني maybe it's logic also. يعني it may be a different way, but I'm not sure if the value will be the same or not. Because now the current is a.
I think will be a little bit more. I think so.
يعني it may be, but يعني the يعني I recommend actually the reference solution يعني because يعني it's confusing a bit now to get the power due to the two cases and subtract. However, if you use the reference way here, يعني it's more logic because we calculated the current. Sorry, we calculated the power loss on the resistance itself. يعني let's read the question here again. يعني compute the annual cost of the operating the motor continuously with the added resistance. So يعني it's not needed to يعني compare it with previous case. We just need the second case. Okay.
Okay, clear.
So يعني it's يعني ايه يعني your solution also or your idea is okay, but يعني it's needed here to calculate only the added cost. Now يا شباب, let's start in another control technique which is V control. We said before we can make voltage control. Again يا شباب, in order to make any speed control we need to check some boundaries or the curve boundaries, which are the curve of torque at small slip, which means the linear part here, okay, from no load, which is very close to that point, to full load, which is a high in this area. So this is the linear part. The other value is the maximum torque. If you neglect R1 in the maximum torque approximately it will be in this shape يا شباب. يعني neglect R1 you will have 3V1 square over 2 omega S X equivalent. يعني R1 is not used in speed control, so we can neglect it all the time. Similarly, S maximum is R2 prime over X equivalent, and NS, which is 120 F over number of poles. Now, these are the curve boundaries. Let's see the effect of increasing volt. If we increase the volt here يا شباب, the torque will be increased. صح ولا غلط؟ مظبوط؟ This is for at any point in the linear part. طيب for T maximum يا شباب, increasing volt will lead to also increasing T maximum. It's proportional to V squared. However, S maximum will be constant. صح ولا غلط? V is not here in the equation. So if you change it or increase the V, S maximum will be constant. NS will be constant as well. So as you can see, if we have here V1, but let's say decreasing the volt, not increasing. If you decrease the volt like that, you will find that S maximum is constant. NS is constant. T maximum decreases. And طبعا torque at any time with the load will be decreased if you decrease the voltage. طيب, what are the benefits and how we can make this control? Let's see the advantages and the drawbacks from the curve here. We can say that S maximum is constant, which means higher efficiency compared to R add. You remember in adding resistance, if you add resistance in rotor circuit, S maximum was increasing. And if S maximum increase, this means the efficiency decrease. So we have here one benefit, which is S maximum is constant. So change the volt whatever you need. You don't have any problem with the decreased efficiency. Number two, the loss is reduced with the with the voltage reduction. Why the loss is reduced, شباب? You know, core losses is proportional to the applied voltage. يعني from the equivalent circuit of the machine, you have resistance of the core here, and you have the magnetization reactance, and then other parameters of the machine. صح يا شباب? So here you have R core, and here you have the applied voltage. So what is the power of core loss? We can say V core equals V line square, or let's say V phase square over RC multiplied by 3. صح? This is the core loss. So if you reduce the voltage, the core loss will be reduced and the efficiency will be increased. So this is another important advantage here. Also, excellent method for starting with T load constant. Sorry يا شباب, not with T load constant, with fan load, مش constant load torque. This is for fan load. I will correct it with the slides. So it's excellent for fan load, and let's correct it now. So not forget to fan load torque. Because torque constant شباب will not work properly here. Why? If torque load is constant, this means you may have torque load at this instant here. So if you decrease the voltage at starting, you may have T starting lower than T constant. However, for fan load, it's suitable for any type. So this is excellent only for fan, not for constant load torque. Fine. What are the drawbacks? Number one, maximum torque is reduced. If you compare with adding resistance, maximum torque was constant. However, if you decrease the voltage here, you can see T maximum decrease. What is the drawback in this case? If you have constant load torque like that, for instance, and decrease the voltage from V1 to V2, this is going to make mismatching between the characteristics. And this will lead to, may damage the machine, because the machine will draw much more current in order to get the electrical torque. So it's not preferred, or it has a drawback of decreased maximum torque, especially for the constant load torque. Number two, limited range of speed control. Can you see, Shabab? Whatever the value of voltage increase or decrease, you did not move in these parts. So you have only speed range from S maximum to NS. طبعا for added resistance, you were able to make much more lower value of speeds. However, here it's not possible. So it's limited range of speed control. This is these are the advantages and disadvantages. But how we can make voltage control? طبعا conventional يا شباب, there were all techniques, like for instance auto transformer. However, it's not used anymore. All what are used now is the power electronic converters. So we can use one of the converters, which is AC voltage controller. It's nothing but back-to-back thyristors like that. And by controlling the firing angles of these thyristors, you can control the output voltage and the current flow. So we control the voltage here by means of AC chopper or AC voltage controller. Right. If the best circuit for this case, let's see the analysis of this circuit together. This is the thyristor يا شباب. Just a brief about the thyristor operation. Thyristor يا شباب is like diode, however it's controlled, which means the diode, how the diode is working يا شباب؟ مين يقول لنا الدايود بيشتغل ازاي؟
It will work if the voltage across it is positive.
جميل. So if we have positive voltage across anode to cathode, it will be turned on. طيب when the diode is turned off يا شباب؟
Of the reverse.
Only?
And I think
the opposite, doctor.
Sorry, again?
The diode will pass the maximum capacity. We cannot control the capacity of the voltage.
Okay, you cannot control, but what is the condition to turn off the diode? When the diode will be turned off?
The opposite, doctor, when applying a minus.
لا, it's not only opposite. It's not a condition to turn off the diode to be in opposite.
To turn off the supply.
لا, it's not like that. And turning off the supply is not a solution. When the current falls to zero, this is the condition. The diode will be turned off only if the current reduced or reach to threshold current, or we can say zero current. So if the current falls to zero, the diode will be turned off. So we have the conditions now, Shabab, of diode. In order to turn on a diode, you need forward biasing. Forward biasing means positive to negative anode volt, anode to cathode. This is the condition to turn on. To turn off, the current should reach to zero. This is for diode. What about thyristor? Thyristor, we have to add another condition for turning on, which is you need forward voltage and a pulse that is going to trigger the gate terminal in order to turn on the thyristor. So for instance, if you have a trigger pulse at this instant here, this is the pulse we have, and assume we have a pulse here. Tafadhal.
Sorry, doctor, but can you repeat the condition for to be
again? Conditions to turn off thyristor. Thyristor, Shabab, SCR. The symbol of thyristor is SCR, silicon controlled rectifier, or called thyristor. To turn on thyristor, you need two things. Number one, to be forward biased. Forward means V anode to cathode is positive. Number two, to have gate pulse, or we can say firing pulse. If you have the two conditions together, you can turn on the thyristor. The condition to turn off is I falls to zero. This is a condition to turn off thyristor. So let's see here the operation, Shabab. We have RL load. We have two back-to-back thyristors. Why two back-to-back? Because one will work in the positive half cycle and the opposite one will work in the negative half cycle. Let's see the operation together if we have positive half cycle. And we applied here at this instant a firing pulse here. So we have pulse here, Shabab. So this means at the positive half cycle, it means U1 is positive here and negative there. So the negative is connected to that point. So this is positive, this is negative. VT1 is forward biased. VT2 is reverse biased. So if you have pulse now on VT1, it will be turned on. So we applied the pulse at this instant. So as you can see, this is, we can consider the pulse like that, Shabab. But in practical ways, it's not like that. It will be just like train of pulses, not continuous pulse like that to reduce the gate losses. Okay, so you have some train of pulses, Shabab. But the instance of starting is the important one. But why we need multiple pulses? This is just if you missed one of the pulses, it may cause a problem, and particularly for RL load. So this is just for protection, to be sure that the thyristor will be turned on. If you missed the first pulse, second pulse will be used to turn the thyristor on. So this is just for protection, in particular for RL load. Right. So it will start working from here. So as you can see, this is the output voltage. When the thyristor will be turned on, it will be like short circuit. So V out and V input will be the same. So U out will be equal to U1. So from here you turn it off on. So I will just make a hashing like that after reaching to this instance. Type at this instant when the voltage drop to zero. Is the current zero or not? Let's see the current together. For the current in RL load, you have R and L, which means that the inductance will store or will be charged if the positive, if it has positive voltage. We have here now two voltages, VR and VL. All of the time, if VL is positive, the coil is charging. If the voltage across the coil inverse it to negative, the coil will be discharged. So for the RL load, you will find that the current will be discharged not at this instant, شباب, but after that. It will take some time or some extra period according to the time constant of the load, which is L over R. So as you can see, the current falls to 0 at this point. So at this point, the thyristor will be turned off. If the thyristor is turned off here now, so in this case, there will not be a current flow and the output voltage will fall to 0. So at this instant, as you can see, the current fall to 0. So the voltage, شباب, is continued in negative part because there was a current flowing in the circuit. Right. After being at this point, now we are in the negative half cycle. So thyristor VT2 is ready to be turned on. However, it will stay waiting the pulse. Here we made firing at instant alpha. So we should make firing for the other thyristor at 180 plus alpha. So this is the instant now, 180 plus alpha. So we made the pulses, as you can see from here. So it will repeat the same operation for the negative half cycle and so on. So comparing the voltage now, شباب, this is the output voltage. Comparing the voltage here with that value, what is the difference?
It is lower.
Lower in terms of RMS, صح كده ولا غلط?
Yes.
طبعا we cannot say average because the average for AC voltage is 0 all of time. تمام? We care about RMS value. So comparing the RMS value of V out, now it's lower than the value of RMS for U1 or supply voltage. So if you now control the instant of alpha moving from this edge up to 180, you can control the firing angle from this instance to 180. So you can get a different value of voltage now يا شباب. ماشي؟ طبعا in RL load you should start firing after certain period or certain angle. What is this angle? This angle we call it as phi. What is phi? Phi is nothing but the load angle. Load angle, شباب, which is the impedance angle. You know, for any impedance, it's Z as absolute value on angle phi. تمام? So this is the angle that you should consider when you fire a thyristor. ماشي شباب؟ طيب here for induction motor شباب, طبعا it's represented by RL load. صح؟ It's not L, it's RL. So for RL load يا شباب, this will be the change of voltage with firing angle. As you can see, V out over V input is moving like that at different firing angles. So this is just a mapping for the voltage control. So you can see you can control the voltage to be up to 0, from 0 to 1 per unit by changing the firing angle. So this is a technique, or this is a method we can use in order to control the voltage. However, this technique is not the most preferred one. Why? Because thyristors made a lot of problems in terms of harmonics. يعني يا شباب, you can see here, we can say we rejected one part of the waveform. As you can see, this dashed part and this dashed part here, it's removed from the waveform. But it's a matter of minus and plus. If you have supply here and you have certain load, okay, and you have converter. Now, if the supply is sinusoidal and you have a device here, okay, and you make the voltage here to be part of the waveform, where the other part, where it will go? It will be reflected يا شباب to other connected loads, or we can say it will be returned to the supply again. So the moved or the removed part from the waveform will be injected to the connected loads, which means harmonics now يا شباب. Because if we analyze the rejected waveform, it will be like harmonics, second order, third order, and so on. طيب, So this means the use of thyristor is not good for because of the harmonics. For that, شباب, there is another circuit for AC voltage controller which is called pulse width modulation. Pulse width modulation. As you can see here, we have not thyristors, we have switches like IGBT, like MOSFET. These are the most well-known transistors used for the voltage control. And as you can see, this is now the operation based on the thyristor. Based on the PWM AC chopper. As you can see, the voltage here, you have many chopping parts. It's not one. And if you can see, we have here 1, 2, 3, 4. It may be many pulses, not one, by increasing the number of pulses, or we can call it as switching frequency. If we increase the switching frequency, you will have sinusoidal wave or the effect of sinusoidal waveform. And as you can see, the current here is almost appear as sinusoidal. And if you increase the frequency more, the current will be very close to sinusoidal. Compare this current, شباب, with previous current. Can you see the current here? Is the current sinusoidal? It's not sinusoidal. It has a lot of harmonics. So this is the aim now of using PWM AC chopper, is to reduce the harmonic contents. For that, we prefer PWM control. So this is why PWM converters are important. يعني, you have already activity number 4. We can say this can be activity number 5, شباب. We need to understand why PWM converters are important. يعني, please prepare just يعني, maximum 2 pages. يعني, I need a report of 2 pages on this activity. يعني, it's يعني, open until the midterm time, inshallah. Okay, so this is يعني, due date is March 15. ماشي شباب.
So you just want like an essay or something about like why do we use them PWM converters?
Yes, يعني justify why PWM converters are important in electrical machines, or even specify induction motor. تمام? Just 2 pages. Okay, what are the circuit may be used, why we prefer it, how we can use it, like that, how we can control it, if there are different techniques, يعني like that, شباب. Okay. Right.
Doctor, what we call this method you mentioned the last slide?
PWM, pulse width modulation.
Yes, but I mean the circuit here. What is it? What do you call it?
This circuit.
It's called
PWM AC chopper. PWM AC chopper.
Okay. Yeah.
This is the name of the circuit.
And
this is PWM. The previous one is called AC chopper. It's based on thyristor. Okay. This is شباب for single phase. For 3 phase, you will have يعني, identical يعني, other 2 phases like that.
Yes.
This is also the same. This is for single phase, and for 3 phase, you will have يعني, other 2 branches identical. تمام يا شباب?
Yes.
Any question, شباب, regarding the voltage control? Everything is clear?
Doctor, here, how to control the amplitude of the voltage?
By controlling something called, this is what I would like you to look for. PWM, the meaning of PWM. PWM, if you control the pulse width, it's called pulse width modulation. By controlling the pulse width, there is a factor called the modulation index, MD. Modulation index or depth. If you control the value of modulation depth, which will be reflected on the width of the pulse, this will make يعني, wider pulses, and the RMS will be higher. So you can control the value of RMS in this way.
Yes. Okay.
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 Any question, شباب?
The frequency will set the same.
Which frequency? In PWM converters, we have 2 frequencies. the output frequency of current, which should be the same of the motor, like here, this is should be, for instance, for the 60 hertz. And you have switching frequency, which represents the number of pulses per one cycle or per second, number of cycles per second. So we have switching frequency. We have switching frequency and output frequency. Switching frequency will be, it may be in several kilohertz, and we prefer it in our work to be higher than 20 kilohertz. Because, if the frequency is lower than 20 kilohertz, your ear can recognize the noise. However, if the frequency increased over 20, you will not feel the noise of the high frequency. So we prefer the range of operation over the 100 kilohertz. And if you increase more the frequency, this is going to help you to have much more better performance in terms of harmonics. Harmonics will be decreased more. Okay, Shabab?
Doctor, the activity, we should write about PWM in general, or we
I will answer your question, but because of the time now, if you would like to leave, Shabab, you can leave. We ended the class now, and we will continue in our discussion if anybody has question, and I will not stop recording. Recording is there. If you would like to see what we have discussed. تفضلوا شباب اللي عايز يمشي. تفضل يا باشمهندس السؤال بتاعك تاني معلش.
Yes, Doctor, about the activity, you said that we should write about PWM. You write in general, or the need of it? Why we use it?
Why we need PWM?
Okay.
For induction motor. Why we need PWM converters for induction motor? Okay.
Okay.
Sorry, Doctor. I think is it used in the inverters? This
yes.
technique about solar
Yes,
regulation?
it's also used in the converter. Actually, converter means power electronic converter, whatever the circuit. It can be rectifier, it can be inverter, it can be AC chopper, it can be DC chopper, it can be cycloconverter. We have lots of circuits in power electronics. Inverters is one of them. However, inverter converts DC to AC. So in order to have DC supply, you need first a rectifier. But for AC chopper, you have AC to AC.
Okay.
Doctor, the same thing for rectifier. We have BW and then.
Yes, you have PWM rectifier as well. We have conventional rectifiers based on thyristors and diodes, either controlled or uncontrolled. طبعا controlled means you use thyristor, uncontrolled means you use diode. However, we have also PWM rectifier. By the way, it's the same circuit of 6-pulse inverter. The same circuit. However, we make different control. We control only the power flow. This is the idle. So the circuit will be the same. However, the control is different. To make it PWM rectifier or PWM inverter, because it's just controlling the power flow direction.
Yes.
Okay.
Also, we can control the output voltage, right?
Yes, sure. The inverter or rectifier, طبعا inverter, the output is AC. So you can control V, you can control F.
Yes.
Rectifier, طبعا the output is DC, so you can control V.
Yeah.
But the advantages of PWM inverters, this is what we need to recognize. Why we need PWM converters compared to previous or conventional converters.
Okay.
Okay.
Sorry, Doctor, I wanted to ask about the diode and the thyristor. Thyristors can be controllable, am I right?
Thyristor is controlled element, yes. And we said, it's already معلش اتمسحت. We said thyristor, in order to control thyristor, and let's have it here. In order to control thyristor, as we discussed, we need forward voltage and we need pulse. So you can control, as you can see, if you make the firing pulse starting from that instant, so the voltage will start from here. So it's controlled element. However, diode is not controlled. Diode is uncontrolled switch.
That means based on the power, the diode will give us the capacity power. The output will be the same as the capacity.
What do you mean by the capacity?
I mean, the power supply will be the same as the power output.
It depends on the circuit. يعني if you have a circuit like that, and if you have AC supply like that, and one diode like that, and here you have RL load, okay, V in, V out. So if Vn is sinusoidal like that, معلش طبعا it's not symmetrical, so the output volt will depend on the current. يعني assume that طبعا the volt will be like that, for instance, starting from here and continue up till finding the current. Now you have RL load, which means the inductance will charge and discharge. It's expected here to have the current like that. The current will start like that and will end maybe like that at this instant. So that the output will be like that. ماشي? This is called rectifier now because we're converting AC to DC because you have DC current. تمام? And it will be repeated on the next cycle وهكذا. So it's up to the circuit.
What about if we use here instead of diode we use the thyristors?
So if you use thyristor now and make a firing at any instant, for instance at here, at this instant, so the current will start from here and the voltage will be appear like that. Okay, and continue. ماشي؟ يعني this is, let's say this is the case of thyristor and this is the case of diode. This is the case of thyristor and this is the case of diode. So thyristor you can control the output voltage. However, diode you cannot.
Can we say that at the end the VRMS of the diode is higher than the VRMS of the thyristor?
Yes, sure. For this circuit, it has to be like that because diode will flow the waveform. However, thyristor will control it. So we can say يعني thyristor, يعني only the thyristor and diode can be or can have equal voltage if the thyristor firing angle is 0, which means you fire at this instant. Otherwise, all of time the thyristor output will be lower than the diode. So we can say V out in case of thyristor less than or equal V out in case of diode. طبعا this is as RMS. تمام.
Okay, thank you, Doctor. It's clear, yes.
Okay. Okay. Any other question, شباب?
السلام عليكم.
Yes.
Okay.
I have a question.
تفضل.
Activity 4, does it have to be a MATLAB code? Can it be Simulink design?
Can it be what?
Simulink design.
Simulink?
Yes.
يعني ماشي, you can make it in Simulink, but يعني you should be familiar in both. يعني writing M5 codes or using Simulink.
Yeah, okay. but I just think I thought Simulink easier, يعني, but if
no
it has to
problem.
be
يعني
MATLAB, I can use MATLAB code.
Whatever you need, but I mean in MATLAB.
Okay.
يعني using MATLAB, whatever M code or Simulink or whatever. But يعني finally I need figures. Okay. Okay.
Thank you.
Welcome. Any other questions, شباب؟ يعطيكم العافية. نراكم على خير إن شاء الله في الأسبوع القادم. السلام عليكم.